In this video, we'll take a look at some of the solutions to the problems from the quiz on section 2.8. So this was the quiz on implicit differentiation, and on the front page of the quiz I was just looking for you to find dy dx in each of the three problems. So in this very first question, it's an implicitly defined relation. It's not solved for y. So to find dy dx, we're just going to take the derivative of the left side of the equation, take the derivative of the right side of the equation, and then try to solve for dy dx. So taking the derivative of x times y squared is going to be a little tricky when you do it implicitly, because what we assume whenever we're using implicit differentiation is that y is a function of x. So this is a function of x, this is a function of x, so we're going to have to use the product rule for this derivative, and the product rule tells us to take the derivative of the first piece of the product, which would just be 1, times the original second piece of the product, plus the original first piece of the product, times the derivative of the second piece of the product. The second piece of the product is y squared. And since y is a function of x, we actually have to use the chain rule to take the derivative of y squared with respect to x. And we're going to do the derivative of the outer function, which would be 2 something to the first. The something is the inner function, which was a y, and then we finish the chain rule by multiplying by the derivative of the inner function, and the derivative of y with respect to x is dy dx. Then we need to subtract the derivative of the natural log of y, and since y is a function of x, we have to use the product rule, or excuse me, not the product rule, the chain rule, and the inner function is y. The derivative of natural log would be 1 over normally an x. In this case it's going to be 1 over the inner function, and then we finish the chain rule by multiplying by dy dx, the derivative of the inner function. We add to that the derivative of 3x squared, which is just a 6x, and then the derivative of cosine of 2x is what we need on the other side of the equal sign. The derivative of cosine is negative sine. And then inside that we're going to have the inner function still, which is still 2x. And then we finish the chain rule by multiplying by the derivative of 2x, which would just be a 2. So we've taken the derivative of this equation now, and it's a pretty big mess here. But we haven't solved for dy dx. We want to try to isolate the dy dx, and then we'll be able to say, yeah, here's our derivative. So we need to solve this for dy dx. So this term, this y squared term, and this term, the 6x, those do not contain dy dx's. So what I'm going to do with those is I'm going to move them over to the other side of the equal sign. So I already have the negative sign of 2x times 2. I've just moved the 2 out in front of the sine function there. I also want to move my y squared over there, and I want to move my 6x over there. So I'm going to have to subtract y squared. I'm going to have to subtract 6x to get them to go to the other side of the equation. These two remaining terms both contain dy dx's. I'm going to factor dy dx from each of those terms on the left side of the equal sign. And if I do that, on this term I'm left with 2xy. And if I factor dy dx out of this term, I'm left with minus 1 over y. So now dy dx will be isolated if I just undo the multiplication between the derivative and the set of parentheses, and I'll just undo the multiplication by dividing each side by the set of parentheses. So dy dx is going to end up being negative 2 sine of 2x minus y squared minus 6x, so exactly what we had there already, all divided by this set of parentheses, 2xy minus 1 over y. So that's the derivative in number 1, done implicitly. The derivative in number 2 is going to be pretty similar to that, just some different components floating around here. Taking the derivative of both sides of this is going to cause us to use the chain rule for the derivative of e to the y, because remember, y is a function of x. So the derivative of the outer function would normally be e to the x. We're going to have to use the chain rule in conjunction with that formula. So we're going to have e to the inner function times the derivative of the inner function. So that's the derivative of e to the y with respect to x. We need to add the derivative of tangent of x with respect to x. The derivative of tangent, we had a formula for it, was secant squared of x. Then we need to subtract the derivative of 2e to the x times y. 2e to the x is a function of x. y is a function of x. They're being multiplied. We're going to have to use the product rule here. Because I need to subtract the derivative of this term, and the product rule contains two terms added together, I'm going to need to subtract a pretty big quantity right here. And inside this quantity, I'm going to have to use the product rule to compute the derivative of 2e to the xy. The derivative of 2e to the x is just going to be 2e to the x times the original second function, which is a y, and then plus the original first function, which is just 2e to the x, times the derivative of the second function, and the derivative of y with respect to x is dy dx. The derivative of 10 on the other side of the equation, pretty nice because it becomes a 0. So just like we did before, now our goal is to try to isolate dy dx. So we have these two terms that contain a dy dx. We want to leave them on the left side of the equation. We want to move these other terms that don't contain dy dx to the opposite side. So I'm going to move the terms to the opposite side that don't contain a dy dx. So I'm going to subtract secant squared of x from each side, and I'm going to have to add this term to the other side to move it over. To the left of the equal sign now, I'm going to have two terms containing a dy dx. Now remember, this one would be negative if we did the distribution. I'm going to factor dy dx out of those two terms. So I'm going to have dy dx times the quantity. Well, dy dx comes out of this term, and we're just left with e to the y. Dy dx comes out of this term, and keep in mind it's negative. We're going to be left with negative 2e to the x. Dividing each side by the set of parentheses to isolate dy dx is just going to leave us with negative secant squared of x plus 2e to the x times y all over the set of parentheses that was multiplying dy dx from the previous line. Sloppy e there, sorry about that. So e to the y minus 2e to the x. Then the last problem on the front page here is actually not a derivative that you need to do implicitly. It just requires two formulas that we looked at in this section. One of them is going to be the derivative formula for inverse sine, the derivative of inverse sine of x. We had a formula that we developed for that, and it was 1 over square root of 1 minus x squared. And then there was also a derivative formula that we looked at for inverse tangent of x, and that one was 1 over 1 plus x squared. I'm just going to have to use these two formulas in conjunction with the chain rule because we have a little bit more than an x inside both of these functions. So dy dx, the derivative of the function y that was defined above, is going to require a chain rule because we have outer function inverse sine, inner function x cubed. Derivative of the outer function would be found using this. So I'm going to have 1 over square root of 1 minus. Now normally I'd have an x squared right here. I'm using this formula along with the chain rule. So I'm going to have to leave the inner function there. And that inner function has to be squared because the x in the formula is being squared. So that's the first part of the chain rule, and then the end of the chain rule would be to multiply by the derivative of the inner function. And the derivative of x cubed would just be 3x squared. And then we need to add to that the derivative of inverse tangent of 3x. So plus, well, the derivative of inverse tangent would be this. But we don't have inverse tangent of x, we have an inner function there. So we're going to use this formula in conjunction with the chain rule. So just like we did before, normally I'd have an x in that spot. I'm going to need to put the inner function in that spot when I'm using this with the chain rule, and I'm going to have to finish the chain rule by multiplying by the derivative of 3x, which would just be a 3. So that would be the derivatives of the three relations on the front of that quiz.